in order to find the domain of a function, you want to look at the function and say, is there any value of x that I cannot plug into this? What would cause me to not be able to plug a value of x in? Okay, so in this first part, we're restricted between 4 and 5. In those numbers, between 4 and 5, would I have any problems between 4 and 5 if I plugged in one of those numbers? No. Would I have any problems outside of 4 and 5? What? 2. If I plug 2 in here, 2 squared is 4, and 4 minus 4 is 0. Can I divide by 0? No, I can never divide by 0. And that's a concept that we have to keep in the back of our minds at all times in this class, because we're going to be doing a lot of dividing by 0 in here. Even though you can't, we're still going to do it. So, between 4 and 5, though, do I have any problems? No. So, I don't have any division by 0 issues here, so the domain is, if I use tabular notation, x values such that 4 is less than x is less than 5. Because I don't have any issues there, so that whole interval, you use interval a lot, is valid. So therefore, what's the range? Remember, the range is all y values that pop up when you plug in all your x values. How could I figure out the range? Plug in 4 and plug in 5. That's right. Plug in our two ends of our interval here. So if I plug in 4, I get 4 squared, which is 16 still. Minus 4 is 12. So that number would be 1/12. So I'm looking at 1/12. If I plug in 5, what do I get? 1/21. Which one's bigger, 1/12 or 1/21? 1/12 is bigger. So 1/21 would go on this side, and my y values or my f values would be somewhere in the middle. So the range is going to be tabular notation. You could say y, but we have f of x here, such that 1/21 is less than. Can it be 1/21? No, because we had this symbol here, so it can't be 1/21. Less than my function, less than 1/12. And that's the answer. So if I plug 2 or negative 2 in here for this bottom part, I've lifted my restriction. Now I have division by 0, which we can never do. So that means that those two numbers cannot be part of my domain. How can I write not part of my domain? I still want to use my tabular notation, though. So it's going to be x values such that what? X not equal to plus or minus 2. Good. Now, to get the range on this one, a little bit tougher, because you can't just plug in plus or minus 2. You'll just get division by 0. So the best way to find the range on this would be to actually graph it and see if there's any numbers that don't work. Because we don't know if 2 and negative 2 don't work, like on the graph. Yes, for x, you can't graph 2 and negative 2, but when you actually graph it, the y values that get graphed, it could be all of them. So it's easiest to graph it. So let me put a quick little sketch of what this thing kind of looks like in here. We have something that does this, and then, oh, I screwed that up pretty bad. Then we have this, and then we have this. Looking at the y values, is there any value of y that it looks like the function never is? Possibly. No? Possibly 0. The function actually is never 0. The value of the function is never 0 here. It would be 0 if if we could plug in what two numbers? 2 and -2, yeah. So, and we'll learn how to deal with this sort of using algebra instead of just looking at it. But yes, in fact, the range here would be all real numbers except for 0. And right now we don't have the math background to be able to do that correctly. But for right now, we're just going to say it would be not 0. So I'm just going to kind of gloss over these. These are in your book. These are your transformations that you've been learning ever since really Algebra 1, although I think for you guys it probably wasn't called transformations in Algebra 1. They are now, though. So we have our original function, whatever it is. It could be y equals x. It could be y equals x squared. It could be y equals sine x. It doesn't matter. This is your original function, whatever it is. If you want to shift it to the right or left, you would include some constant that you're adding or subtracting inside that function. So it would be y equals x plus 2 squared if you wanted to translate your parabola left or right. 2 units. Vertical would be adding on a constant on the outside of the function. So that's like your y-intercept sitting right there. That one's pretty easy. I think you guys get that one. Reflections, all you have to do is, what's this notation trying to tell you? Negatize everything. Yeah, you're substituting in either a negative for the entire function to flip it, or you're substituting in a negative x for the entire function to flip it about the other axis. And we kind of worked on that. Symmetry with respect to the x-axis and y-axis, same kind of idea. If you can reflect it about those, then that's what you do. For a parabola, if you had y equals x squared, if you wanted to reflect that over the x-axis, you would go y equals a negative x squared. And if this is y equals 2x squared, then reflect it with the negative 2x squared. Reflected about the origin, you substitute in a negative and a negative for the function, so y becomes negative, a negative for the x, so x becomes negative. And then you simplify it down, and then it's reflected about the origin. Like I said, you can find these in your book. You don't really have to furiously write them down, but the important thing here is you can use any of these in any combination with any others as many times as you want. So, these are combinations and compositions of functions. I have two functions here, f and g, and these are also in your book somewhere. The following are true. I can add them together, and that's part A. If I want to add them together, this might be the notation you would see, and really all you're doing is taking f and adding it to g. Combine like terms, and then you have f plus g. The same thing is true for subtraction. This is the notation you would see. This is what you would really do. You would take f minus g. And what I'm going to tell you is get in the habit, if you're not already, of putting parentheses around that function when you do that math. Subtraction is always tricky because it's really being addition multiplied by a negative 1, if you want to think about it that way. So the whole thing is being subtracted. Some of you will make that mistake. Notation for multiply would be f times g. There's just an fg there. There's no symbol in between. Notice the difference between this one and this one. This is multiplication. This is not multiplication. So just be aware of that. F times g is really just f of x times g of x. And that's where you're going to wind up using FOIL or the distributive property or the box method or whatever it is that you want to do to multiply polynomials together. F divided by g, kind of an obvious one there. F and g look like a fraction. And really all you're doing is taking f, dividing it by g. And we'll deal with long division, synthetic division, and rationalization a little bit later on. E, this one's fogged, and you also have Goff. Some people like to prefer them that way. F composed of g, when you see this circle, it looks like a degree sign. That's called, as you read it, it would be composed of. So that would be f composed of g of x. And what it really means is you're taking g of x and you're substituting that whole thing in everywhere you see your variable in f of x. That's all that is. And then you simplify it down from there. So if you have exponents or whatever, you'd have to multiply them out or FOIL them out or whatever. We have f of x is 2x minus 3. This is a very simple example. G of x is x squared minus 1. Find these things. For the first one, f plus g, what am I going to do? Just add them, right? So here's f, 2x minus 3, plus x squared minus 1. And then we will need to do what? Simplify it, yeah. Combine like terms. So I'm going to start with my highest degree, which is x squared. And then I have a 2x and no other x's, so plus 2x. Then I have a negative 3 and a negative 1 for a total of negative 4. So there's my answer. X squared minus plus 2x minus 4. For f minus g of x, same thing. Same order even. 2x minus 3, but now it's a minus sign. And when you put that minus sign in there, automatically you should be thinking what? What? Parentheses, thank you. Substitute in x squared minus 1 with parentheses. That should help you keep that minus sign straight, because otherwise you're going to screw it up and you'll leave off a minus sign for that negative 1 and it will stay negative. It isn't. So we have the same idea going on here. It's a negative x squared. That's still a positive 2x, but now it's negative 3 minus negative 1 for a total of negative 2. There's the answer. F times g of x, this is basically going to be a FOIL problem. So we have 2x minus 3, x squared minus 1, and we're just going to multiply them together. So 2x times x squared is 2x to the third, then minus 2x, then minus 3x squared, and plus 3. Combine like terms. You can put these in descending order if you want to. Just for the sake of space, I'm going to leave mine just like that because there are no terms to combine. F divided by g of x, same idea here. We're going to take f, which is right here. That's my numerator. And divided by g, which is my denominator. And that's the answer. You don't have to go any farther than that, because even if you could factor this whole thing, you wouldn't be able to form any fancy ones. This factors into x plus 1 times x minus 1. There's nothing to pull out here, so there's nothing to get rid of. That's the answer. F composed of g of x is probably the one that you struggled with if you were struggling at all. What I do is I turn this into f composed of g of x right away. I do that because then it makes it obvious. I'm taking g and I'm going to plug it into f. So I'm going to start writing f, and every time I hit a variable, I'm going to plug in g. So here's f 2 times x, but x turns into this, x squared minus 1. Then I continue writing f minus 3, and now I'm done writing f. So now I need to just distribute or FOIL or whatever it is that I need to do. In this case, all I have to do is contribute that 2 in, so it becomes 2x squared minus 2 minus 3. Combine like terms, 2x squared minus 5. So this is your basic review of what graphs look like. You have a bunch of different polynomial functions sitting here. We will probably deal with all of these at some point or another in this class, along with trig functions and their graphs. So it's best to just know what they look like when you see them. This would be a constant. Give me an equation for this line right here. No. No. Y equals y equals 1.5. That's it. Is there a variable in here? Why not? What do we call something that never changes? A constant. Hence, a constant graph. Okay? There's no variable. If there's no variable, it's a constant. It's steady. There's no variable. Y equals a constant. That's it. Linear. Give me an equation for this guy. Okay, y equals. So we need the slope, right? Here's a nice easy spot. Here's a nice one. So my slope is 3/2. Now what? X minus 1, okay? Algebra right there. That was like your favorite day when you were able to pull equations from graphs in Algebra 1. Can you give me a quadratic equation for this graph? Y equals negative x squared plus 2. What transformations are present here? Translation and a reflection. Good, that's it. No dilation here. How do I know there's no dilation? Well, I didn't write a coefficient here. How do I know by looking at the graph that there's no dilation? No. If you know the pattern from the vertex, over 1, down 1, over 1, down 2, 3, over 1, down, whatever, okay? So if you know the pattern for these, then you can recognize when there's no dilation or when there is. All right, a cubic function, I'm not expecting you to be able to give me an equation for this, although you probably could if you thought about it. And I'm not going to write one up here because I have no idea what it is, and I don't really want to think about it. But the idea is, this is a cubic, it looks like a snake. This is a quartic, or a fourth degree polynomial. It looks like a W. This is a quintic, or a fifth degree polynomial. And it's back to looking like a snake, okay? Now, what is the degree of a constant graph? 0. How about linear? 1, quadratic. We're just going by the exponent, right? The degree of the polynomial. 4, 5. What do we know by looking at these graphs about how each of these graphs behaves before we even see the graph? How many they could have. How many x-intercepts they could have. A 0 degree has how many x-intercepts? Unless it's actually y equals, and then the whole thing is pointless. A linear function has how many x-intercepts? Does it always have 1? Is there a linear function that could have 0? Not of 1 degree. This is technically linear, but it's a 0 degree. Okay? So, a linear 1 degree has a slope to it, which means it has to cross the x-axis. How about quadratic? It doesn't have to, but if it did, it would have to, or. So we have 0, we have 2, we have 1. If the vertex was exactly here, then we would have exactly 1 x-intercept. How about cubic? How many can we have here? We can have 3. In fact, we do here. Can we have 2? We can have 2. Can we have 1? Can we have 0? We can't? Can we have 0? Is everybody sure?
Well, until you prove us wrong.
You have no choice. There has to be a root, okay? There has to be an x-intercept here. You can have 1, you can have 2, you can have 3. You can't have more than 3, and you can't have 0 with this guy. How about a quartic? You can have 4. You can have 2. Can you have 3? There's 1, there's 2, there's 3.
You also have 1. Or you have 0.
Could you have 1?
Yeah. Go down, touch it. Yeah, touch it. Just translate that 1 you drew.
Very good. You can have 1 here if I just touch here and then it does that. Okay? So, you can have 4, you can have 3, you can have 2 like this graph has, you can have 1, can you have 0? Yes. How about quintic? What do you think? Yep. What about 0?
No.
Okay, so do you see the pattern here? For odd degree functions, what is true? You can't have 0. That's right. For odd degree functions, it looks like a snake. For even degree functions, it looks like could be a W, an M, an N, whatever. All right. The point is, if we start in one direction with an even degree polynomial, we're going to finish in that same direction. If we start in one direction with an odd degree polynomial, like way down here, we're going to finish on the other side of the graph, way up here. Or vice versa. We could start high and do some stuff and then finish low. We should be able to answer all of these. End behavior. Anybody remember what the actual, yes? Okay, that's what we write. What is end behavior? What the graph looks like, or what the function does. Let's put that. What the function does. What, me?
No.
What?
Just because he didn't write in cursive?
It was just funny, like, what the function does. Like, that's our, like...
That's our definition?
Yeah, definition.
Well, I'm not done.
I know.
Don't laugh until you hear everything. Well, okay, so end behavior is what the function does when.
The rest will just be this quickly.
Right, yeah. And that's it. Alright, so what the function does when? As, I like the word as, that's good. Now let's pick some different words.
It approaches the line of the graph.
As x approaches, not just infinity though. Right. Positive infinity and negative infinity. Is infinity a number? It's like a state of mind. It's not really a number. It just means as we grow, positive infinity would be forever going this way. And negative infinity would be forever going this way. So as the function goes out into enormous numbers in either direction, how does the polynomial behave? All right, so let's use this information and talk about the degree, the leading coefficient, and the end behavior for these graphs. So first of all, what do you suppose the degree would be here? Probably 2. What would the leading coefficient be? And I'm not talking about the number, I'm talking about the sign. Probably positive. And the end behavior here is going to be as, so in algebra 2, this is how we would write it. As x goes to infinity, the function also goes to infinity. As x grows infinitely this way, the function is growing infinitely in the positive direction. So that's what that means. Now as x goes to negative infinity, so now we're letting the function, we're plugging in values that are going infinitely this way. What is the function doing? It's going to positive infinity. The function goes off to positive infinity. So it's still positive infinity. The domain here. Yep, there's no numbers that I can't, there is no numbers that I can't plug in. Pay no attention to my grammar. How about the range? Are there any y values that don't get graphed? Right, everything less than 0. And I'm just being sloppy here. It's y values such that y is greater than. Can we have 0 or no? Yeah, we can have 0, so it's greater than or equal to 0. All right, the degree of this guy, it's a snake, it looks like maybe 3. Leading coefficient, probably positive. We are going up from left to right. If this is a line, you would have a slope that looks like this, and you would say that's a positive slope. Same thing holds true here. We're going up from left to right, basically, so that's a positive leading coefficient. End behavior. Okay? So negative infinity, the function goes to negative infinity. Domain, any x values that can't get graphed? Okay, so it's all real numbers. How about range? All the y values are getting graphed here, so this one's all real numbers. Okay, what's the difference between the top graph and the bottom graph? It's flipped, yeah. It's reflected. The leading coefficient, therefore, is negative. The degree here is still 2. The end behavior now is, so these guys would be, this should actually read negative, and this one should be negative as well. So I'm not going to really go through writing all that because it takes forever, but they're both negative. How about the domain? Any change? Nope, still all real numbers. And the range flips that too. So it's y is less than or equal to 0. And over here, what happened here? So this is a, what kind of transformation? It's a reflection. Yeah, it's a reflection. So the degree is 3. The leading coefficient is negative. The end behavior is switched again. So now we have negative infinity and positive infinity. The domain and range are still all real numbers. Okay, so this example here just illustrates that the degree dictates what type of graph shape you have. The leading coefficient dictates how it behaves from one side to the other. So we kind of talked about this one already. How many zeros for odd degrees are we going to have? What's the lowest number of zeros we can have for an odd degree function? 1 through the degree. And for even? 0 through the degree. So odd functions, you're guaranteed to have at least 1 0, which is always nice. All right, what's our end behavior here? And what is our odd or even? And tell me the number of real zeros. Go.